Okay, as a final step of this chapter, we're going to take another closer look at the binary symmetric channel. So we assumed before that the messages that are being passed are actually Gaussian messages. And we may wonder if this assumption is valid in the symmetric channel, because in our analysis of the Gaussian approximation, we assume that the messages that are being passed in the decoder, they are Gaussian distributed. We took a look at this message evolution for a decoder. So we actually looked at the probability distributions, and we saw that at least the variable to check node distributions, they are nicely Gaussian. Check to variable node distributions, they are kind of peaky and not so much Gaussian. So we may wonder what happens for the binary symmetric channel. So let's take a look at how the situation looks like for the binary symmetric channel. So this is a repetition. So what we have is the following. We calculate the channel transition log likelihood ratios following way. We have L of y given x is log of 1 minus delta for delta if y is equal to 0. Or it's minus log of 1 minus delta for delta if y is equal to 1. Or it's y double dot, so the transmitted, the received value, times LC, log of 1 minus delta over delta. This we multiply by the received noisy value. So in our analysis, we assume that the all zero code word is transmitted. So we fix and we assume that x is equal to 0 is transmitted. So then we can calculate under this assumption the log likelihood ratios. So we can calculate the probability, so the log likelihood ratio. So let's start with 1. So L of y equals y given x can only take on two different values, plus or minus LC. These are the two only possibilities in the binary symmetric channel. So we take a look at the probability that L is equal to plus LC, given that x double dot is equal to plus 1. And this is equal to 1 minus delta. This happens with probability 1 minus delta, we receive actually a plus 1. But in this case, when we receive a plus 1, L is equal to plus LC. Now, if we receive a minus 1, then L is equal to minus LC. Probability that L is equal to minus LC is equal to delta. So we can write the distribution of our log likelihood ratios in the following way. It's essentially a direct, we have two directs. So we have one direct, and here we use uppercase delta because we already used lowercase delta, the error probability, which is slightly not so nice, but this is what it is. So with probability 1 minus delta, we have a direct at plus LC. Direct is shifted by L minus LC. And with probability delta, we have a direct at minus LC. So let's take a look at how this looks like. So for different deltas, if delta is large, we have a direct at plus LC. So this would be plus LC, and this would be minus LC. And we have another quite large direct minus LC. And you see they are very close together, and from the height, they are also pretty close to each other. Now, when we make the channel better, so what we have here is f of L given x equals plus 1, and here is L. When decrease delta, so the channel becomes better, this is the situation. So the directs move a little bit further apart, and the height difference becomes more significant. So this one becomes higher, and this one becomes smaller. And if delta is 0.2, situation looks like this. If delta is 0.1, situation looks like this. Plus LC and minus LC again. And again, they move further apart, and the height difference becomes slightly different. And like this. And this is for delta equals 0.01. We have a big delta, a big direct of probability 0.99 at 5, which is log of 1 minus delta over delta, and a direct of 0.01 1 at minus LC. So this is summing up everything. So the deltas, they move closer to, or the directs move closer together if we increase deltas of the channel becomes unreliable or less reliable, and the height difference becomes smaller. Okay, so now this goes into the decoder. So what happens in the decoder? So we start an example and we look at a regular code, just 3.6 LDPC code, and delta is equal to 0.05. So the variable nodes to check node, they just send the channel messages, this one and this one. The check to variable node messages, they transform these using the hyperbolic tangent operation and so on. And this is, you also get two directs out. Why do you get two directs out? Because essentially you have the absolute value of the directs. The absolute value is plus or minus LC. That doesn't change. So you also get plus or minus LC. They move a little bit closer together because the value is changed with the hyperbolic tangent function. And you get essentially two directs out with a decreased height difference, so they're less reliable. Now you're going to send these towards the variable nodes. Then in iteration 2, we have the following situation. So in iteration 2, now we get more possible combinations, because now we have the channel clock-like iteration plus minus LC, and we have those two. And now we have multiple combinations. So we can have plus LC from the channel, then we can have two of these, one of these, we can have three of these, 0 of these, we can have one of these, two of these, and so on. So all possible combinations, and this leads to multiple different cases, and these are the 6 directs that we get the output. Then again, we go to the check nodes, and the check nodes, they calculate some values, and you get, again, more possible combinations. And these are the directs that you get after the check to variable nodes. It starts to become a little bit messy. And now what you do after 3 iterations already, the variable to check node messages, they look like this. So you have an awful lot of combinations. It really starts to explode. So it's like a combinatorial explosion. You have an awful lot of possible combinations, and all of these combinations, now you take all the possible combinations at the check nodes. And there are so many that my computer crashed when trying just to draw the number of directs. There were just too many directs, and the compiler of the figure started to crash. So we need to take a different approach. That's why you don't see directs here, but you see an empirical distribution. This is what the distribution looks like. So how do we get from a direct to empirical distribution? So to do this, we take a look at an example. And the example is, we look at the empirical distribution. So let's assume, simple example, we have a PDF f of x, and we have a direct at -1, and we have another direct at +1. Both of height 1/2. So then the cumulative density function f of x looks like this. So we have 0, and then we have a jump 1/2 at -1, and then we have a jump from 1/2 to 1 at +1. And we can, of course, change this jump by now interpolating. Instead of having this jump, we interpolate. And then, of course, the PDF is the derivative of this. This would be a uniform distribution here. So this is kind of how you can approximate it. Now, this approximation works much better if you have many of those directs. So let's look at a second example where you have many of those directs. And let's say you have directs that look like this. So they are uniformly spaced here in this range. This would be f of x, so CDF. And the CDF would look like this. So let's say the CDF then would look like, so we have these tiny steps. And these steps become smaller and smaller until you reach one. And now, of course, you can approximate this, and I use a different color. You can approximate this by a line, and you get a uniform distribution. And now if you have directs that are spaced not uniformly, but spaced according to some pattern, this is a way to empirically model a distribution of directs using a continuous approximation. Usually it's done the other way around. So you model a continuous approximation using a set of directs. This is called particle filtering method. And this is actually how we computed the PDFs in the previous example for the binary input AWGN channel. So let's assume we have directs that are, we have a small, some directs here, and then they are very closely spaced, and then they are less closely spaced again, like this. So then let me try to draw f of x. So f of x then looks like this. So here we go, upwards, then up, we go up, we go up, and then so we go up here, we go up here, and then here we make a few more steps, and then we go up here and one more here, like this. So we can approximate this one by that goes more smoothly like this, and we'll have a distribution that will look something like this, exaggerated. So this is a smoother approximation. So this is how you can empirically approximate sets of directs with continuous functions, just by having a smooth approximation for this. And this is essentially what we did here. So instead of plotting all the directs, we did this smooth approximation, and this is the curve that we got. And this is what we're going to continue. So after 3 iterations, it looks like this, and we also do the same approximation for the variable node to check node messages. So instead of having this set of directs, which is really difficult to see what's going on because they're so closely spaced, there's so many of those here, but they have very low amplitude. We do this continuous approximation, and this is the distribution as it looks like. Then we go to iteration 4, and this is the approximations that we have. We go to iteration 5, iteration 6, and it starts to look very, very Gaussian already. It's a little bit tilted, so it's not really Gaussian. This is more Gaussian, so let's let it run for a few more iterations. Iteration 7, iteration 8, and here we start already getting direct plus infinity, but you see the message approaches pretty nice Gaussian already. And after 9 iterations, we have converged. So this is the empirical approximation, and we see this Gaussian approximation still holds, at least after a few iterations. So we make some mistake in the first iteration where the approximation is completely wrong, completely off. But after a few iterations, the Gaussian approximation starts to hold. And then it's actually quite a good approximation, and we can use it successfully to model the behavior of the decoder. So, conclusion, the Gaussian approximation is also approximately valid for the binary symmetric channel. So we make significant mistakes in the first iteration. This explains possible differences. We could track the evaluation of the full PDF, but it's difficult. What we did here is this Monte Carlo evaluation. And if you like to replicate this, we have a MATLAB script. So the support of the discrete PDF, unfortunately, very quickly explodes. The PDF becomes quasi-continuous. So analyzing the behavior of the decoder for the binary symmetric channel, unfortunately, is not a very easy task. If you want to do it consistently and rigorously, it's going to be very tough. But if you say, I can rely on the Gaussian approximation to get a good first estimate of what's going on, then the Gaussian approximation is the way to go, because it will give you a very good first guess of what is going on and what to do. So with this, we're at the end of the chapter. We have some supplementary material here that you can do in self-study. We have this very nice proof of the gap to capacity theorem. And with this, we reached the end of our analysis chapter. The next chapter, it's called Analysis and Design. This is reminiscence of previous. We put the design means the degree distribution design. And we now know how to analyze LDPC codes, how to design distributions. The next thing we're going to look at how to design parity-check matrices and how to some more practical aspects of LDPC codes. But we will do this then in the next year. For this year, we finished. And this, I wish you a very nice Christmas break. And I'm very happy to see you again next year.